The second speaker is Dr. Minhyuk-san. So Minhyuk is an assistant professor in the School of Computing at KAIST. And before joining KAIST, he was a research scientist at Adobe Research. And he received his PhD from Stanford University under the supervision of Professor Leonidas Gibas. And his research interests lie in vision, graphics, and machine learning with a focus on 3D geometric data processing. And his work was featured at SIGGRAPH Asia 2017 for a press release. And today he will give a talk titled Discovering the Compositional Structure in 3D Shapes from Supervised to Unsupervised Learning.
Okay, thank you. Thank you for the great introduction. So today I'm going to talk about discovering the compositional structures in the 3D shapes. So I'd like to start my talk with some high-level ideas. So we know that many objects we are seeing the daily lives have these structures that decompose the object into the multiple parts. So basically, the objects can be decomposed with some semantic labels with the names that they call the parts, and also with the parts that have some different ways of interacting with the people. Basically, the functionality, some parts can be some areas where the people grabs with the hands, or the other parts can be or the places where the people sit. So all the parts of the objects can be also defined based on some some appearance information, like some materials or the textures that are assigned to the parts, or based on the mobility, basically how the parts are articulated and moving. And the idea of understanding this the object from the composition structure, basically its parts and their arrangement in the space, is a the old idea that has been investigated for a long time, from back in the 1970s. Basically, the 1970s was the time when the pioneers of the computer vision and the cognitive science, like Thomas Binford and David Moore, basically first they conceptualized the idea of recognition by the components, basically perceiving a object by seeing it as the arrangement to be some simple geometric components. And this idea has been evolved for a long time in the history of the computer vision and the machine perception to better basically perceive the objects. And using the composition structure in the 3D modeling and also the editing is also very common in the computer graphics and the CAD applications. And most of the CAD and the 3D modeling tools are basically designed in a way that the user can basically place some small and the basic components in the space and composite them with some the operations like the CSG operations here to create the final completed shapes. So when basically dealing with some of scan data, also solving the reverse engineering problem, basically recovering this some structural information from the raw geometry is also very important problem to enable many applications like the shape editing and the manipulations. And also in the robotics, learning such the compositional structure is a essential task. So for the autonomous agents, it is not sufficient to just recognize the object, but the agents need to know how to interact with objects, like which parts you should grasp to open the, for example, open the door, or pour the water from the bottle, and what is the place in a cup to pour the water, basically. So these are basically some information about the parts of the objects, and we need to know how these parts are basically arranged in a object. So, and to learn this this structure of the information, basically the 3D data would be basically the best type of the data, since basically it matches the physical form of the actual objects. We can basically describe the objects as it presents in the real space. So unlikely with the images, basically when you deal with the 3D data, you don't need to worry about basically the viewpoints or the occlusion or some variations coming from the different lightings. So you can, for example, this directly discover some the part structure by for example fitting some bounding boxes, or detecting some primitives, or discovering some symmetries or some repeating patterns, or finding some common components across the different shapes in the same category. So along the direction of learning some compositional structures in the 3D shapes, recently there has been lots of the work, especially based on the neural networks. So PointNet is one of the base architecture processing this 3D data, which can also segment the input point cloud into the multiple semantic parts. And especially the segmentation has been more actively investigated in the case of handling some scene data. And people will solve both the semantic segmentation and the instance segmentations based on the scene training data like the TT data set or the ScanNet benchmark. And more recent work basically focused on the learning this kind of the part structure even without having any supervision, but by just fitting some sort of the some primitive shapes like the bounding boxes or the superquadrics, were more complicated, some kind of the convex shapes. And also such effort was not limited to some human-made objects or the scenes, but also extended to some non-rigid, some kind of the deformed shapes like the human bodies and the animals. So in my talk, I'm going to introduce some my recent works all about the learning the composition structures in the 3D. So one is about the primitive fitting, and I'm going to explain why the supervised learning is basically needed in this kind of problem, and what would be the kind of the best way that we can leverage some supervisions in the primitive fitting. And the second one is about the unsupervised method that can learn the decomposition of the parts using the deformations. And the last one is basically about the weakly supervised method that can learn the semantic parts from the shapes, but without any ground truth the semantic segmentations, but from some language descriptions of the entire shapes. So let me start with my first work, which is the supervised learning for the primitive fitting. And here, let me first briefly introduce the exact problem that I'm going to solve. So here the problem is that given a 3D shape, which is represented as a point cloud, so we are finding a set of the geometric primitives that can best describe the input shape. So as here, and also we consider 4 types of the primitives, which are the planes, cylinders, and spheres, and the cones. So let me turn on the razor here. Okay, cool. So yeah, and the output should basically include the number of the primitives, and also the types of the primitives, and also the parameters of the primitives, and also the supporting areas in the input point cloud to each of the primitives. Basically, why we solve this problem? So this is very fundamental problems in the computer graphics, and also these days the 3D scanning and the CAD industries are very much interested in this problem. So this is basically the reverse engineering problem, basically converting the scans into the CAD. But obviously a CAD file can contain some more complicated information that just kind of having the primitives, but this can be still kind of the first step, like converting the scans to the CAD. So here what I'm going to say is that despite the big advance in this 3D scanning the technology, the lack of this kind of some converting tools, like converting the scans into the CAD, basically became a kind of the bottleneck to extend the applications of this scanning the technology, since the raw point cloud cannot be used in many applications like the shape editing and the manipulations. So the scanning industry has dealt with this problem actually by providing a kind of manual service. So basically they hire some kind of the expert the CAD designers, and they let them create a 3D model that can exactly match the scanned shapes. And basically these are the names of the companies that provide this kind of the service. And as you can imagine, basically it takes huge amount of the time and also huge amount of the cost because everything is basically manually done. So basically we want to have a kind of the fully automatic the pipeline that can do this kind of the scan to CAD conversion. And such kind of the reverse engineering is also needed not only for the scan data, but also for some kind of 3D models in the online repositories, since most of these 3D models that we can see in the online the databases are basically typically represented as kind of the meshes, basically the vertices and the faces, and the original the CAD information is basically missing. So this kind of like recovering the CAD information is also very important to exploit the 3D models in the many in the online repositories. So basically, if you see this problem, this is basically is kind of just primitive fitting problem that you can just apply any kind of some typical some estimation techniques like the rank set and the half transform. And also actually the technique that is known as kind of the state of the art for this primitive fitting problem before actually our method is also the rank set based method, which is called the efficient rank set. And this efficient rank set is actually kind of nothing but just kind of iterating the rank set multiple times for each of the primitive type. So you randomly sample some of the points over the input point cloud and define a primitive. And if it has the sufficient number of the inlier points, then you take the primitive and also take out the inlier points. And you just repeat this process until there is no remaining points. So this, and also this algorithm is also implemented in the CGAL, which is the famous geometric processing library. So you can try this algorithm yourself. And here the point is that actually this is a kind of the estimation problem that we can actually solve without the neural net. So let me actually quickly remind the difference between the prediction problem and the estimation problem. So for the prediction problem, like classification or detection or the recognition, basically in the test time, we cannot measure the correctness or the quality of the outputs. So basically to measure the quality or the correctness of the outputs, we need some kind of the extra information, which is typically not given in the test time, but only in the training time. So this the extra information in the training time is basically the supervision. So we train the neural net to memorize this kind of the patterns of the what is the good answers for the inputs. And based on the kind of the inductive bias that the neural net learns, the neural net can basically predict the good answers without the measuring the quality of the outputs in the test time. So these are the big problems that we typically solve with the neural net. But in the estimation of the problem, basically there is a way that we can measure the goodness of the output in the test time. So without basically any kind of a learning process, you can basically solve a optimization problem and find the best model that optimizes the evaluation function. So in the primitive fitting case, the evaluation function can be the distance from the primitives to the input point clouds. So basically the distances from all the primitives to the point cloud are very small, then we can say that the output primitives basically regularly construct the input shape. So this is basically a problem that does not require any kind of the supervised learning. Then why we talk about the supervised the learning in this case? So here the issue is that the estimation, the problem that we are solving is basically ill-posed, meaning that when you find the solution based on the criteria, basically the distance from the primitives to the points, the best solution with respect to this criteria may not be the solution that we want to see. So here the example is that we have a shape of the board which has the top, the part which has the 6 side planes here. But depending on some small random noise added to the input point cloud, actually the best solution, minimizing the fitting error from the primitives to the point clouds, can be the case of splitting the single plane even into some multiple small primitives, or it can be the case grouping the multiple side surfaces into the one cylinder. So these are basically all the possible cases minimizing the distances from the primitives to the points, depending on the noise which are basically presenting in the input point cloud. But here actually the solution that we want to see is having exactly the 6 side planes here. So this means that the reconstruction error, the distance from all the primitives to the points, may not be the best measure to capture the sort of the people's expectation, having the 6 side planes in this case. And if we also use the rank-based method, the only way that we can handle this kind of sensitivity to the noise with the method would be basically to fine-tune the rank-set the algorithm parameters, such as the fitting errors, the fitting error the threshold, or the crossing the threshold. But this kind of tuning or tuning the parameters requires lots of the human inputs, so it becomes impossible to make any kind of the fully automatic pipeline. So here we propose an idea of leveraging some supervision to better solve this problem. And this is the work that we published in the CDPR 2019. And before we go into some details of how to leverage this supervision, let me first explain how we acquire this kind of information. So in our setup, basically the supervision comes from a large-scale 3D CAD model data set. So the basic idea is that we basically synthesize the 3D scans by sampling points over 3D models and also adding some random noise. So we also show that our network trained with this kind of synthetic data can also work well with the real scan data. But here, basically, the benefits of using this kind of the synthetic point clouds created from the 3D CAD models is that we can basically take the full supervisions from the 3D CAD models. So we can have not only the ground truth information about the primitive parameters, but even more we can actually have some even more information about the shapes. So we are going to develop a neural network that can fully exploit all these informations coming from the CAD models. And going back to the algorithm, so here the key question is basically how are we going to design a neural network for this kind of supervised learning? So for that, one option would be still train the neural net with the same reconstruction laws, basically the distances from the primitives to the input point cloud as same as like running the rank-based pipeline. But then, no, there's nothing different with the rank case. So basically, we're going to see the same, the ill-posedness problems that, basically the neural net falls into the local minimum. And the other option would be basically predicting the parameters of the rank set in the rank-based pipeline. And this is also not easy problem because the iterative process, like taking some primitives and removing some inlier points, these are basically non-differentiable the process. So for training the neural net, we actually might need to use the RL-based the approaches to solve the problem. And the other option actually would be directly regressing the primitive parameters. But this is also not easy problem because neural net is not good at basically solving this kind of the regression problems, basically predicting some absolute informations. So here, our key idea is that instead of like directly somehow predicting some primitive parameters, we predict some intermediate attributes using our neural network and then map this information to the final primitive parameters with the kind of the differentiable function. So for example, so here this is basically the naive case when we have the input point cloud X and also the neural network F, which is basically directly predicting some of the primitive models, the primitive parameters. So this is the naive case, and we are going to change this formulation like this. So here the G is the new neural network, which is not predicting the primitive parameters, but some sort of the intermediate attributes. And now this kind of the output, the attributes are mapped to the final primitive parameters using the given and the fixed function H. So this H is not learned, but this is kind of the given differentiable function. So here the idea is that basically we are finding the best primitive parameters from this kind of intermediate outputs, this GX, by solving a kind of the optimization problem. And actually this function H is basically the analytic solutions for the optimization problems. And the good thing of like having this kind of change of the formulation is that now we can have some kind of the extra loss functions for the intermediate outputs, the GX here, based on the supervision that we can get from the CAD models. And these new loss functions actually play the critical role of making this formulation to be well posed and also improving the quality of the outputs. So if I show the diagram of the architecture, so this is the naive case that we are directly regressing the primitive parameters. Now we want to switch this architecture like this. So here the output of the neural network is this intermediate the attributes here. And this is fed to the function H here, which is not learnable function, but this is given and the basically fixed and also differentiable function. And this function actually outputs the final primitive models, but the primitive parameters Y here. And since this given function H is differentiable, the good thing is that we can also run the backpropagation from the end to end of the pipeline in the training. So I also show in the experiments that how much this kind of the end-to-end training is important in the performance. So now let me go into a little bit more details about the neural net architecture. So there are 4 main parts. So at the very beginning, we take the input point cloud and then process this point cloud using the backbone architecture. So here we basically use the PointNet++, but any architectures processing the point clouds can be used here. And these parts basically returns 3 types of the per point attributes. And basically these the attributes are the intermediate attributes that I called in the previous slide. And these 3 the per point, the attributes are basically the labels for the primitive, the segmentation, and the labels for the primitive, the types, and also the point normal information. So basically the first 2 are basically solving the problems of the instance segmentation and the semantic segmentation. And so from these 2, we can basically decompose the input shape into the parts and also decide the types of the primitives. And the last one is basically the first derivative information of the geometry, which is especially useful to estimate the axis of the cylinders and the cones. So once we have this kind of the per point information, the intermediate attributes, in the next step, now we compute the primitive parameters that best fit the each of the segmented parts. And here, since now we know how the input shape is exactly segmented into the parts and also know the types of the primitives for each of these segments, and given the types of the primitives, we can solve the optimization of the problems for the fitting. And now we can also even derive analytic solutions that minimize the fitting error from the points to the primitive surfaces. So we are basically, the idea is that we are basically figuring out this sort of the segmentation problem at the first part, so that we can make the problem easier in the rest of the pipeline. And the analytic solutions becomes the differentiable function h here, which is mapping the intermediate attributes to the the primitive parameters. And so this is the basic idea. And I'm not going into some details in the formulation, but you can check out some details of like how we derive this kind of the analytic solutions in our paper. And once we compute the primitive parameters, now we need to compute the fitting losses and also other losses. But for that, actually, the thing is that there is no basically the fixed order of the primitives. So the order of the ground truth primitives that we have in our the training data can be different with the order of the output primitives. So we don't have any information like which primitive should be the first and which primitive should be the second and so on. So since we don't have this kind of the order information, what we need to do is that we need to match the ground truth primitives with the predicted primitives. So for that, what we do is that we basically reorder the output primitives by computing the fitting errors for all the pairs of the ground truth primitives and the output primitives and find the best one-to-one correspondences. And for these pairs of the ground truth and the output primitives, now we compute the loss functions. So for the loss functions, we have the fitting loss, obviously. And as I mentioned before, now we have some supervised losses for the three types of the intermediate attributes. And this supervision basically comes from the CAD models that are basically used to synthesize the input point clouds. So we basically have the three more loss functions, which are the segmentation loss and also the type classification loss and also the normal loss. And additionally, we also use one more supervision, which is basically the axis of the some of the primitives, like for the cylinders and the cones. We also have some extra loss functions for the angle of the axis. So when you train this network, we can get this kind of the output. So these are some examples of the results. And this is also a comparison between the results of our framework on the right-hand side and also the result of the rank set-based method. And this is one of the actually very challenging case that we have two very close cylinders, which are the inside and the outside of this kind of thin part of the shapes. And these two surfaces can be very easily confused in the rank set-based pipeline, but our framework can precisely distinguish these two surfaces. And this is another challenging case that we have two cylinders, which also the radii are almost the same. So the rank set-based method cannot see that there are actually two cylinders here, but our framework can easily segment these two. And this is another case that we have some multiple small cylinders inside this kind of the big green plane. So this is one of the also the challenging case that we have some very different scales of the primitives. Like one is very big and the other one is very small. But also even in this case, our network can successfully find all the small primitives and also the big primitives. And this is also the quantitative comparison showing how many points in the input point cloud are basically explained by the output primitives when we basically vary the threshold for the distance. So in this graph, basically higher is better. So compared to the case of like the rank set-based method, the rank set-based method is the blue line. And also the case that we are directly regressing the parameters using the network, which is the red line. So compared to these blue lines and the red lines, you can see that the method like combines some predictions of the neural net and also the optimization gives some way better results with some very huge gap in this graph. And despite also the domain gap between the training the data that we are using, which is basically the synthetic point clouds and also the real scans, we also found that our network actually works well even with the real scan data. So here are some of the examples that we are basically finding some very tiny and the very thin primitives from some real scan data of this kind of the mechanical parts. So here basically we show that how a supervised learning can be leveraged to solve a kind of the estimation, the problem, basically fitting the primitives to a point cloud to improve the performance. And we also show that the 3D CAD models can be used to provide some kind of the extra to the supervision, which is actually especially very useful in this case to make the problem much easier. So this was the first part. Do we have any questions for this first part? Now let me move on to the second part. So yeah, now let me move on to the second part. So in the second part, actually, I'd like to talk about some deformations. So actually, the composition of the structure that we are discussing now is actually also very important to make some variations of the shapes. For example, here, when you know that this airplane is decomposed into the two wings and the one fuselage here, then we can try to, for example, like translating like the wings like this and also elongate the fuselage. But if we don't have such kind of some semantic the part information, then sometimes it's not easy to create some kind of the some realistic and some plausible some deformations. So without the part structure, actually we can still try to make some deformations with some deformation handles. There are lots of the techniques like using some control points like here or some kind of the cage meshes here to make some deformations. But the limitation of such kind of work in the perspective or like making some user interactive some tools is that it does not guarantee that the output of the deformations basically makes sense. So for example, what I'm going to say here is that when we have some kind of key points of the chair like this, we know that like the bending the leg toward the left or the right, like here, we're just pulling down like one leg while keeping all the other legs is kind of like breaking the chair. So we are not making the chair as kind of a chair. So the chair with this kind of information won't look like a kind of the another chair. So to make some kind of the plausible deformation, basically they make the chair like the chair, we need to know like some kind of semantic or some structural information about the shapes. So here, our goal is to basically learn some kind of the intuitive or some kind of the some user-friendly some deformation handles that are also aligned with some kind of semantic meanings and also produce some kind of the plausible deformations. So we also propose to learn this kind of intuitive handles without any supervisions about any kind of the semantics or the structures, but by just kind of learning from a large collection of these 3D shapes in the same category. So let me first show some examples like the output of our neural network. So each of the columns on the right-hand side here is the outputs of our networks. So our network basically predicts some kind of the intuitive handles that deform each of the parts in the shapes. And as you can see, like basically the first one is kind of like repeating the C part, and the second one is kind of like raising the armrest, and the third one is kind of like the tilting the back part, and the first one is kind of like changing the width of the chair, so and so on. So there are kind of many other kind of the handles here. And our learned is kind of the deformation handles are also kind of the consistent across all the shapes. So based on that, a user can also edit a collection of these shapes simultaneously. So let me also show our demo basically editing the 3D shapes. You can actually also play with this demo in the link, which is encoded in this QR code here. So you can basically see that there are multiple some deformation parameters that are learned by our the neural network on the right-hand side here. And every time when the user basically moves these kind of sliders, you can see how each part of the shapes are basically changing here. And these changes are also very consistent across all the chairs, despite the kind of the different structures of these kind of the shapes. And here also, the most interesting part is that we do not use any kind of information about this kind of the parts, and also there are kind of the semantic deformations in the neural net training. But the neural net is basically self-supervised in a way to learn about like what would be kind of some natural way of like factorizing the deformations into some interpretable some deformation handles from the given collection of the data. So here we see how basically the neural net learns the underlying some part structures of each of the shapes and how to decompose the shape into these some multiple parts. And this is our work, which is published in the CVPR last year. And let me explain the high-level idea of this work. So as the input, basically we take a 3D shape and also some geometric deformation of the deformation handles. So as the input handles, we use some random control points that are automatically created using some farthest point sampling algorithm. And using the bounded biharmonic coordinates, we basically can define a deformation function from each of the key points, the FC here, that basically describes how the entire shape should be changed when you move each of the key points here. And the deformation function defined with key points is basically the linear. So we can represent this deformation function as kind of the matrix, the W here. And our goal here is to produce a set of the new deformation handles based on the given the deformation handles. And these new handles are basically defined as a kind of the linear combinations of the given deformation functions, given the deformation functions which are defined with the contour points. So this is why we call the new handles as kind of the math handles. So the neural net basically outputs the linear combination weights of the given contour points for each of the math handles. And actually, we can interpret this as kind of like predicting some basis vectors in the space of the given the contour point parameters. So for example, here we have the C number of the contour points, which and then basically this means that we get the C times 3 number of the parameters because every point can have the three-dimensional coordinates. So in this space, we are basically predicting m number of the basis vectors, which become our learned math handles. So basically, we want to find a set of the basis vectors in the given parameter space, so that each basis vector becomes aligned with some kind of symmetric part and their deformations. And we also enforce these basis vectors to be independent of each other, and still also make them to span a kind of the linear subspace in the given the parameter space that can only include some kind of the plausible deformations. So this is basically the basic setup. Again, the inputs are basically the input the shapes, and also the randomly sample the contour points over the input shapes, and also the deformation function defined with the given contour points, which are basically the biharmonic coordinates. And our network first predicts the set of the linear combination weights, basically that define each of the meta handles here. And also here, the thing is that actually we can think this as kind of the setup of the conditional generative models. So once we have the set of the meta handles and also produce some kind of the random deformations based on the meta handles, we can actually add a kind of the discriminator that tests whether the deformation created by the meta handles are basically looks like the real or the fake. So precisely, we are predicting not only the set of the basis vectors, but actually we predict a kind of the distributions over the given the contour point parameter space, so that when you sample randomly sample any points over the distribution, then these parameters can create kind of the realistic shapes through the deformations. So if we consider this as kind of the conditional the GAN model, so here the condition is basically this input shape. But here the difference with the typical conditional GAN model is that in our case, the generator is not learned, but actually this generator is given. Basically, in our case, this generator is kind of the deformation, the functions defined with the given the contour points. So what we do is that we actually not learning the generator, but given the fixed generator, actually we are learning the distributions of the plausible shapes over the given the deformation the parameter space. So this is kind of the one difference with the typical generative models. And the other difference with the conditional generative model is that in the typical conditional GAN, the thing is that the domains of the input and the output data are basically different. So we can consider some models like converting black and white images into the color images, or some daytime images into the nighttime images, or converting a sketch into the some real images. And these are basically all the cases that when the input itself cannot be a kind of some any kind of the desired outputs. So basically, you need to make any changes in the input to make a kind of the realistic outputs. So when you convert the sketches into some real images, the sketch itself cannot be a kind of some real images, but you need to make some kind of the changes into the input to make a kind of the real images. But the problem in our case is that the input and the outputs are in the same domain. So which means that both the input and the outputs are the 3D shapes in the same category. So if you do not make any deformations, any change into the input, then this input itself actually becomes the perfectly plausible shapes, the perfectly plausible the output data. So if you use a typical conditional GAN setup in our problem, here the problem is that the neural net does not learn any deformations because the input itself is the perfect the outputs. So the learned the distribution in our case also actually becomes a kind of the sort of the Dirac delta functions, which picks is at the zero deformations. So what we do here is that we basically add another module called the Deform Net here, which basically randomly picks a target shape in our database and try to match this kind of target shape by making some deformations based on the learned method handles. So basically, in order to match the random target shape, the distributions over the control point of the parameter space should not be a kind of the sort of the exact delta function, but it should be kind of expanded to cover all the random target shapes. So basically, this enforces that the learned distribution to include all the possible deformations. And as the loss functions, we use the multiple loss functions, both for the geometry and the disentanglement. So I'm going to skip some details here, but here we use a kind of the regularization loss that disentangles the statistically independent some deformation factors into multiple method handles. And this actually loss function plays the important role of like discovering some symmetric parts and their plausible deformations. So let me skip some animations here. And as I mentioned, we also have a website where you can play with this kind of demo yourself. So please check this out. So here I introduced like how we can create a conditional subjective models that can learn some kind of the plausible deformations, and also deformation handles that can produce some plausible outputs, like some changes of the shapes without having any supervisions about the parts and their structures. And also I briefly mentioned that how the symmetric part, the structures can emerge from the learning the independent factors of the deformations. So I'm already running out of time, so let me go quickly with the last part of the presentation. So actually, the last part is also about the 3D segmentation, but based on the language description. So we know that the 3D annotation is actually quite challenging and also time-consuming. So while the data annotation itself is very time-consuming task, actually it is especially very challenging in the 3D case because it requires also some kind of skills like playing with some kind of a 3D interface. And also the annotation is not done by just making some few mouse clicks, but actually you need to change the viewpoint and annotate the shapes from the multiple directions. So these challenges in the 3D annotations might be actually one of the reasons that why we don't see many of the large-scale data sets for the 3D shapes with the annotations. For example, MS COCO data set, the data set with the images basically include more than 300,000 images with annotations, but for the PartNet, which is the more recent data set, including 3D models, actually has like only 27,000 models, which is like 10 times smaller. So here, what we propose is that we propose a method that can learn the symmetric parts only from the some language descriptions of the entire shapes. So what we do is that actually we collect the descriptors of each of shape from the some mechanical Turkers, and this is the way easier task for the Turkers than directly annotating over the 3D shapes. And also even to make this process even easier, for the Turkers, we provide some references to the as kind of the shapes. So basically these tractors are the references, and we are asking the Turkers to describe this target shape so that this target shape can be discriminated from these tractors. So what we exactly do is that we are having a speaker who describes the target shape, and then we are also having another person who is the listener who can identify the target shape from the destructors. So this is basically the setup, which is called the reference game, introduced in this paper, ShapePlot, published in the ICCB 2019. And the goal of this work, the ShapePlot, was to actually create a neural speaker and also neural listener, basically the neural net speaker and the neural net the listener that learn from this kind of the human speakers and the human listeners and imitate the process, basically describing the shape with the language and also understanding the language to identify the target shape. So the goal of this work is basically to make some neural network that can learn basically the connections between the natural language and the 3D shapes based on the data collected in this way, based on this kind of reference games. And in the architecture of the neural listener, basically the neural net takes a utterance, basically a language description, and the three other shapes. And one is the target shape, and the other are basically the structures. And the network basically classifies the target shapes using the architectures like this. So if I just briefly explain the high-level goal of this work is that basically if we have the kind of for example, the utterance of the leg here, then the neural listener here basically finds the leg from the shapes. So when the input shape looks like this, we are basically making the neural network so that it can first find the parts that we need to see, basically to identify this kind of target shapes. And then we actually, for this kind of the process of finding the parts, we are using a attention module that can basically highlight the regions that we need to see to make this kind of the discrimination. And the neural listener is basically seeing this part and then finding the target shapes across this, among these kind of three shapes. So we are not only finding the target shapes among these kind of given shapes, but also we find like which part is described in the given the language descriptions. So we are basically discovering the semantic parts from the very weak supervisions, which are basically these kind of the language descriptions of the very holistic representations of the entire shapes. And this is the work which is actually not published yet, but under review now. So let me skip some details of this work because I'm running out of time, and let me just go into some results here that, so these are some results. So the left one is the input shape, which is actually pre-segmented using the method called the BSPNet. So BSPNet can, accurately somehow detect all the boundaries of the parts, but it's kind of like over-segmenting the input shapes. So it's over-segmenting the shape into the many small pieces, many small the convex shapes. And on the right-hand side, these are basically results when the network is trained, even without any, the semantic, the segmentation as the supervisions. So these are the same case. There's some cases that our outputs actually are basically matching the ground truth, but here are also kind of some of the failure cases. In the ground truth, there is no armrest, but in our case, we are finding some of the armrest here. But actually, this might be even more kind of the natural the outputs that we are having the armrest here. So this might be actually the case that even the ground truth may not be correct. And these are some other big examples. And also there are some kind of the failure cases that we are having some lag part here. But actually, it also makes sense that we are having some lags on the bottom of the chairs. So we are, and also for the other cases, we are also almost perfectly matching the ground truth without having any supervisions of the semantic segmentation. And also some interesting result is that while we train our network only with the chairs and the descriptions about the chairs, the network can be also generalized well to the other classes of the shapes. So this is the examples that we are finding some semantic parts of the tables when you train the network with the chairs and the descriptions of the chairs. And this is also another case that we are finding parts of the airplanes using the network, the same network trained with chairs. Okay, so let me skip some details. And so in this work, basically, we show that the language descriptions of the holistic some representations of shapes actually can be used to discover some of the semantic parts. And for that, I skipped some details, but we made a kind of the careful design of the attention module so they can discover this kind of the part segments through learning the attentions in the case of the identifying the target shapes from the distractor shapes. Okay, so in summary, I introduced 3 different works that learned the composition structures from the 3D shapes. The first work was about the supervised learning and leveraging the full supervisions coming from the CAD models to fit the primitives to the 3D shapes. And the second one was about the unsupervised learning, basically finding the part structure by learning some plausible deformations of the 3D shapes. And the last one was about some weakly supervised learning, and we showed that the part segments can be actually discovered only from some language descriptions of the entire shape, but without having any kind of the semantic segmentation supervision. So here my takeaway messages is that I just wanted to give some my answers for these kind of the high level questions. So the first question about what sort of the supervisions can you use for learning this kind of the compositional structures? And I showed some examples using some full supervisions coming from the CAD models, and also using some language descriptions as kind of the weak supervision. And for these cases, I also explained some ideas about what would be kind of the best ways to leverage this kind of supervision. And for the first case, I also showed some examples combining some best features of the neural net, the predictions and also the optimization. And the second one was the case of using the attention module to learn from this kind of the weak supervision. And the last question is about how can we even guide the neural network to learn this kind of the composition structure even without the supervisions. And also I provide the kind of the examples like decomposing shapes while learning the shape, the variations, the deformations, but there can be also multiple other ways of learning some the decompositions in a kind of the unsupervised way. Okay, so this is the end of my talk, and I will be happy to take some questions.
Thank you very much. Thank you, Minhyuk, for the great talk. So now we are in the Q&A session, and I think we don't have any questions from the audience yet. So let me start start with my question. So about the third method, about the language-based segmentation. So in my understanding, it can handle objects with a few parts, like 2 or 3 parts in my understanding. And I'm wondering whether it is possible for the network to handle objects with even more number of parts or finer grained parts.
Yeah. Yeah, that's a great question. So actually, the reason why we just found some kind of the coarse-grained parts is that actually, from the data that we use, basically we use the language data collected from the shape plot. But when you see the data, basically most of the utterances that we use, they do not have any kind of some descriptions for the small parts of the chairs. So people typically try to see kind of some big parts to basically see the difference between some kind of the chairs. So that was the main reason that we could not find some kind of small pieces of the parts using the based on our method. But what we tried is that if we have some kind of the language descriptions for the small pieces of the object, then our method actually could find this kind of some small parts. So what we tried here is that since we did not have any kind of some language data, we also synthesized this kind of the language data by actually having this kind of some finer grained parts, which are annotated in the data set called the partnet. So we synthesized some kind of some language descriptions based on this kind of some kind of the partnets that are used in this partnet. And when you use this kind of some synthetic language data describing some small pieces of the parts, actually we could find some kind of some small some parts like this. So we could actually find some of the some subparts of the kind of the components that we found. Like, so we could find some like kind of some small pieces of the leg or some kind of slats of the chairs, and also kind of some small pieces in the tables like this. So our method could actually find this kind of some fine-grained parts, but actually the limitation was that actually we could not actually somehow guide the talkers to make some kind of descriptions about these small pieces. So that would be also kind of the one of the future work in this work.
I see. Thank you. We have it's almost time, but I think we can accept one more question if the audience have. Probably no. Okay. So let me ask the last question. So quick question. So about the first method, about the fitting, primitive fitting. In my understanding, the method assumes a fixed set of primitives, like spheres or plane. So my question is how difficult it is to support like parametric surfaces, such as knob surfaces or like that.
Yeah, that's also a really good question. So actually, I couldn't prepare a slide for that, but actually, our kind of the future work of that direction was to actually handle some more complicated kind of types of the primitives. Actually, there is another work which is it's kind of the follow-up of our work. I forgot the exact name, but actually there was kind of another follow-up of the paper which was basically dealing with the nerve surfaces. Actually, and also along with this kind of the 4 types of primitives that we used in our work. And we also did another project, which is also handling some extrusion cylinders. So we are not just finding these cylinders, but actually we are basically making some of the primitives by having some 2D sketches and extruding this 2D sketch into the 3D space. So that was kind of the way more complicated types of the primitives. So we also basically extended the idea to handle this kind of some more complicated types of the primitives, but still there can be more. There can be some more types of some many complicated types of the primitives, and there will be still kind of the lots of things that we need to do along that direction.
I see. Thank you. Thank you very much.